Thank you. Is recording now? Oh my gosh, I forgot. I thought this, I will change the setting after class. I thought this class is setting as like automatic recording. I forgot. Thank you for reminding me. It's recording now. So for the statics review, so the main thing we need from the statics is the free body diagram calculating internal force. So for the free body diagram, first we need to have the outline shape of the structure. So it's basically the structure from free from the boundary condition. So let's say if a structure has a wall clamped on one end, the free body diagram should be free from the wall, and there's a reaction force applied on this structure. So it's the body for free from constraints. Second step, for having the equilibrium equation, we do need to establish the common coordinates. So this coordinate can be global XY coordinate. We mainly focus on 2D problem. If it's 3D problem, it's XYZ coordinate. It can be the global coordinate. We should always, normally we put left, right, upward, and out of plane, or into the plane direction as XYZ coordinate. But we can also use the local coordinate, which means that, let's say if I have a structure that is inclined direction, and for each calculation, of course, we can use the x direction at the local x direction. So you can use any coordinate that you want. The final answer will be the same. Structure will fail or not, does not depend on coordinate system. Coordinate system is just for your calculation. And of course, we normally want to choose a coordinate system that is most convenient for our calculation. We can talk about this part in detail using our example problem later. So a convenient coordinate system. The third one is show the force, all the forces at the moment. The first one, of course, is the external applied force. So let's say for this 1D bar, I have tensile force on this end, on the free end, and it's clamped on this side. So basically, of course, this tensile force applied on the free end is the external applied force, right? So when you do the free body diagram, make sure that you have that force on the free body diagram. And the other one is reaction force. As I said, you need to be free from the constraint, so separate from the walls. And now you put reaction force on the clamped end. Reaction forces. And of course, these reaction forces, it depends on the different situation. let's say if it's 1D bar problem and you only apply tension on the free end, this reaction force provided by the wall, we know that it's in the actual direction, in the opposite direction, right? So you have tensile, you have tensile force applied at free end. So reaction force should be also in the actual direction. In the opposite direction, same magnitude. This is for 1D bar situation. But let's say if it's a clamped beam, kind of a beam problem, I clamped on one side and apply transverse force apply a couple at a free end. Now the reaction force, it becomes for this 2D problem, it becomes reaction force in the X direction, reaction force in the Y direction, and a reaction moment. Makes sense or not? So even though it may seem like the same structure, based on different external force, it may be 1D bar or the 2D beam problem, and the reaction force can be different. So we can talk about in detail later. The third one is the internal force at cut surface. Again, let's always use this simple example. If I want to know the internal force at this point, so you learn from the statics that what we need to do is we need to have a cutting surface passing through this point, and now we have the section of the structure. So now for this cutting surface, it has the internal force, right? So, and of course, if it's 1D bar, we know internal force is in the actual direction. If it's beam problem, we know that internal force, including the shear force, tensile compressive, the horizontal, if there's a force in the horizontal direction, and the bending moment. So this is the internal force at cutting surface. If we need to figure out the internal force inside the structure. And the last one is the weight. I want to say that in the real structural engineer problem, you a lot of time you need to consider weight, of course. But for the mechanics materials, the practice problem, most of the time we ignore the weight, unless we really say that we need to consider weight. So weight of the body, when necessary, we need to consider it, but most of the time we can just ignore it. So this is showing all the forces and the moment. And then we do need to indicate all the dimensions. The necessary dimension. So this is for writing in the force equilibrium equation, you need to write the moment equilibrium. And for the moment equilibrium, you do need the moment arm. So make sure that you have the dimension there, so you know what the moment arm for writing the moment equilibrium equation. So these are the major steps for doing the free body diagram. So when students actually doing the free body diagram, there are several parts that they most likely just get confused. First is the reaction force. So in what situation, what kind of reaction force exists? So in terms of reaction force, I want to put some details here. For example, if we have a structure what kind of reaction force it will provide? In what direction? How many components? Anyone? For a reaction boundary condition like this, one reaction upward, yes. So in this situation, it's rotor support, so it only has the reaction force upward. Right. And if it's a how about this one? Pin joint. It's the same or different?
Two reactions.
Yes, thank you. Now you should have reaction force in the x direction and the y direction. Another common situation is, I'm sure you guys have seen this a lot. So it's the, what kind of reaction force here? It's clamped.
3.
3. Yes, thank you. So basically we have the reaction force in the x direction, reaction force in the y direction, and we also have a moment. Reaction moment, right? So before doing the free body diagram, we should be very clear that what each kind of boundary condition means and what kind of reaction force it will provide. So these are the most common three boundary conditions. The first one is rotor support. So this rotor support means that it's free to move in the x direction, but it cannot move in the y direction. So when it constrains the degree of freedom in the y direction, it must provide a reaction force in the y direction to constrain the movement in the y direction. So this is the rotor support. For the pin joint, it means that it's free to rotate, but it's not allowed to move in the x direction, does not allowed to move in the y direction. So to constrain these two displacement in x and y direction, they need to provide reaction force in the x direction and reaction force in the y direction. And the last one, it means that when it's clamped, it means that it cannot move in the x direction, cannot move in the y direction, it cannot rotate. This one, pin joint, it can rotate. This one, it cannot rotate. So the actual reaction force is the reaction bending moment. Reaction bending moment can be, I will talk about this one later. Actually, let's say, for the reaction force direction, it really doesn't matter which direction I put here. I can use x, y. Let's say this is a positive bending moment. This is what you want to say, right? Yes, of course. You can do it in this way and write the equilibrium equation. And let's say if your final moment, you calculate the bending moment is a positive number. It's a positive number. It means that your reaction moment is in the same direction as I put here. If you calculate the moment reaction force, here is a negative number. It means the direction of the reaction moment is in this direction. So the moment, well, it can follow the coordinates. So this is a positive x, positive y, and a positive rotation. But you can also put it in this way. And depend on the number you get at the very end, it will indicate, combined with the initial direction, you can identify the actual direction of the moment and force. Did I answer your question? I can talk about in detail later why, like how to put the direction of the force, reaction force, and reaction moment. Yeah. So now these are the three commonly used if you want to know the like the complete more complete boundary condition reaction force kind of thing, this is a screenshot from statics textbook. It's not content of mechanics materials, it's really the content of statics. So this is the rotor support, and if there's a cable, well, if it's cable, it can only have 10 tensile force. If it's this link, it has tensile compressive, but both of them need to be in this direction. And this one, the reaction force is always perpendicular to this direction or this rod direction. And this is a pin joint. It's the same as what I said here. It's a pin joint. So it's free to rotate, but it's not allowed to move in the XY direction. So it can be here, the reaction force in X and Y. But of course, it can as given as one force, but you also have the unknown angle here. This is a fixed support. It's same as what I said here, the clamped. So it does not allow to move in X, Y, and does not allow to rotate. So that's why we have a extra moment. So this is a screenshot from the statics textbook. If you are confused about any part, come to my office. We can talk about this one in detail. So now let's get back to for equilibrium equation, how to put the reaction force direction. So in free body diagram, the sign for the unknown reaction force, we have two ways to do it, or the direction of the unknown reaction force. The first one is assume direction by inspection. So again, let's say if I have 1D bar problem, I just use this simple example to help you understand this part here. Let's say you have 1D bar, you apply tensile force on this free end. You know that reaction force, yes, it's unknown, but you know that reaction force applied by this wall should be in the opposite direction, in the same magnitude, right? So for this situation, you can just like, by inspection, you know the direction of the reaction force. So let's say if it's 1D bar, you have tensile force applied at a free end. Then you know that the reaction force should be in this direction. So let's say this is the point A, then should be in this direction. And then you do calculation, of course, you have force equilibrium and you get the number, positive number, and the positive number means that the reaction force is in this direction with that magnitude, which is the same as this one. So a lot of times, just by inspection, we know what the direction reaction force is, and we just put it there directly. It does not always need to be follow the coordinates positive direction. And the second situation is that for a more complicated situation, you don't really know. Let's say, again, it's still the same structure, but I apply different force. Let's say I apply this real force on top. And apply a couple at the free end. Apply tensile force. I have all these force applied. I have force in the X direction, I have force in the Y direction, I have bending moment. So for the reaction force at the wall, we know that, well, we know that there are three components: force, negative force in y direction, and force and moment. But we don't really know, without a calculation, we don't really know like which one is in which force in which direction by inspection. So a common method we use that we put everything in the positive direction based on the global coordinates. So based on global coordinates, we know that this is the reaction force in the y direction. This is a positive AX, and this is a positive moment, reaction moment. So we just put everything in the positive direction based on the coordinates. And now we use this one to do the calculation. And again, if you calculate, let's say for this one, if you calculate negative value, it means that the actual reaction force is in the opposite direction of this positive x direction, right? If you get a positive value, of course, it's same direction. And same thing for the moment. If in the end, if you get a negative value, it means that the actual reaction moment should be in this clockwise direction. If you get a positive value, it means that it should be the same as what we assumed at the beginning. So this is for a more complicated situation. If we cannot determine the reaction force direction just by the inspection, we put everything in the positive direction and do the calculation. So these are two ways for the reaction force, how to put a direction in the free body diagram. And of course, I want to say that, let's say some students in this situation, they say, okay, I know that just by inspection, I know the reaction force, let's say the reaction moment, I know is in this direction, just by inspection. And somehow, the calculated negative value is okay. The assumed direction by inspection could be wrong, but in the end, you can still get the correct answer because it also depends on the positive and negative number you get at the very end. In the end, your final answer is correct. So it really doesn't matter. Like you can do either by inspection or positive direction. So this is for reaction force. Another one is the internal force. So I want to have this part separate here because this part it used to be very confusing for a lot of students. Some convention for the internal forces. Again, let's assume that this is the global X, global Y. For tensile compressive, this one is simple. We know that tensile always generate positive internal force and compressive always generate the negative internal force. Let's say for a bar AB. So if we want to figure out the internal force at a specific point in this bar, we have a cutting surface through that point. So now we have two sections. One is the left side, one is the right side. So let's assume that it's cutting through point C. So now this is the left side. We have the AC section. So on this cut section, we still have the external applied force N applied at A. Now for this cutting surface, let's put as use different color. Now this become a positive surface. Now this one is internal surface, is internal force. and this is positive. And the same thing, if we take the right section, CB, let's use different color. Now this becomes a negative surface, and now this one is the positive internal force, even though it's in the negative x-axis direction. So this is a positive, the red surface means positive surface because it's facing the positive x direction. And the green surface here is a negative surface because surface is facing the negative x direction. So now for the internal force, this one is positive internal force. This one is also positive internal force. Now, of course, tension compression is the easiest one. The next one is bending. I hope you guys still remember in the statics, this is considered as positive bending when bending upward. So let's assume that the external applied couple, they're like this, M to generate this positive bending. And this is the beam structure AB. And again, I want to know the bending moment at this point. So we have a cutting surface passing through this point. Now, again, we have the left side and right side. So now on this positive surface, this is a positive internal bending moment. But of course, when we talk about bending moment, it means the internal force. This is the external M applied. This is the A point, this is the cutting point. And same thing at the right section. We have, this is the B. This is the cutting surface. Now this is the negative surface. And on this surface, this is the positive bending moment. And externally applied M here at B. So again, as you can see that for the internal force, it really does not follow the coordinates. It's not just always in the positive direction positive, because now you can see that on this negative surface, now in the negative x direction is a positive internal normal force. This is a positive internal normal force. And the same thing here is counterclockwise, but on this surface, this is a positive bending moment, right? And the last one is a shear. Again, in statics, it defined that if you have a shear force applied in this way, and you have a C point in between. In statics, it defined that if these two shear force, transverse force generate a clockwise rotation of the structure, it will cause, it defined as a positive shear. So if we have, again, let's say that if we want to know the shear force at this point, at point C, and we need to have cutting surface about passing through this point. So again, left side, right side, we have AC. This is a positive surface since it's facing the positive x direction. And on this surface, downward shear force is a positive shear force. AC. and external applied force actually put it here. And for the right section, now the internal shear force positive is upward. Now this is a point C, B, and I still put the external applied force here. So definition from statics, from mechanics materials, we consider on this positive surface. Positive surface means that the surface is facing the positive x direction. Positive surface, positive surface, positive surface. This downward shear force is defined as a positive shear force because this one generate clockwise rotation of the structure. And on this negative surface, because the surface facing the negative x-axis, and upward internal shear force is considered as the positive shear force. And of course, I want to say that this is a definition of statics and mechanics materials. If you go to higher class, like the aerostructure, Mach 1, FEA class, definition will be different, but we only consider when you take that class. But now, for now, this definition is okay. I just want to make sure that do my best to be consistent with textbook. So this is our definition of the sign convention of internal forces. This is very important because when you do the free body diagram, you do need to put correct direction of the internal force on the free body diagram. This is not like the reaction force. Reaction force, it doesn't matter because if you calculate positive value, negative value, you combine with the pre-assumed direction, you always get the correct direction of reaction force. But this one, it has to be in this way. So this is something I hope you guys can. Yes, so everything I put here to consider the positive, and if it's opposite, of course, it's negative. So let's say this, I use this one as example. So if I apply compression, now on this surface, positive surface is this one is the negative normal force, internal normal force, and now this one here is negative internal normal force. Everything I put here, they're positive because this is a positive, tensile positive, bending upward is positive, and this one generate shear is positive. Any other question? If no question, we are done for the class today. I will continue with example problems in the next class. Or you can come to my office hour if you have any questions. Thank you for coming and have a great day.
Thank you.
You're welcome. Thank you.
Thank you.
You're welcome. Have a great day.
Thank you.
You're welcome.